remote. Our first speaker will be Ram Senior, and he will be talking to us about context-bounded safety verification of thread pools in multi-threaded shared memory programs. Yes, please. Thank you.
Thank you all for coming to this talk. The title is a mouthful. It's an expanded version of the actual title of the paper, but we will get into it one by one. So this is joint work with Pascal Baumann, Rupak Majumdar, and Georg Zetscher. We are all at the Max Planck Institute for Software Systems. So the setting is that of verification of multi-threaded shared memory programs. So let's see what these are. First off, I would like to say that these programs occur in operating systems, web servers, databases, embedded systems, in a lot of different places. And as you can see, there are multiple threads which are running. And so each of these threads has its own local Boolean variables. Um, and it also has a stack to model recursive calls that the thread makes. And there is a global state also consisting of booleans here x1 and x2, which is shared between all of these different threads, right? So this is how they communicate with each other. And one of these threads, as highlighted in green here, is the active thread, and the other threads are inactive, right? So the active thread is the one which is currently making moves. The other threads are still waiting. Additionally, there is a task buffer which consists of uninitialized tasks, which will be converted into threads at some point. So what are the operations that you can make in these programs? So one set of operations is the thread operations, namely, given the active thread, thread one, this thread can change its local Boolean variable value. For example, here y1 is changed from 0 to 1. It can also change the value of the global Boolean variable x2 here, for example, to 0. And it can also push and pop its stack. So here, for example, it pops this top of stack. Right? And the last thing it can do is spawn new tasks, which are just added to the task buffer. And so that was for the active thread and what it can do. The other thing that one could do is to switch threads. So here, thread 1 is currently running, and instead we switch over to another thread, thread 2. And there is a non-deterministic scheduler which at every time point decides which thread to run. So this is part of the model. So now instead of switching threads, we could also choose to run a new task. So for instance, here when we switch away from thread 1, we start thread 4 where one of the yellow tasks in the task buffer is started. And to summarize the important model features, there is dynamic spawning of new tasks. There is recursive function calls which are modeled by stacks. There is the ability to model program features such as locks using global Boolean variables. And the local Boolean variables can model parameters and return values. Right? So this is the setup. And now the natural question is in this setting, what are the properties that one can decide about such programs? And unfortunately, most properties are undecidable already for just two recursive threads. And this is because two stacks already gives one a Turing powerful model. So the natural question is, what kind of restrictions can we place in order to get decidability? So in this paper, the restriction that we place is called context boundedness. So in order to understand context boundedness, let's define the notion of context switch numbers. So here we note that there are these numbers written in green below each of the different tasks. Some are running in threads and some are uninitialized. So the uninitialized ones always have a context switch number of 0, whereas the tasks which are currently running in threads, they will increase their context switch number from 0 as they keep getting switched in and switched out by the scheduler, right? So here, for instance, suppose we move away from thread 1, then this context switch number 2 of thread 1 increases to 3, right? And in this setting, in this case, we have started a new thread. We have initialized one of the yellow tasks, and its context switch number does not increase. So now, instead of running this new task, we could have chosen to switch from thread 1 to thread 2. So in that case, the thread 1 would still increase from 2 to 3, but thread 2 would remain at 1, right? Its context switch number would not change. So now we can define the notion of a k context switch bounded run, which is one in which every task is swapped out at most k times. So this leads to context bounded analysis, which has been done since the 2000s by various researchers. And it is, of course, an under approximation of system behavior, but it has been shown to be useful in practice in order to find bugs. So, for instance, one can study the safety problem with this restriction, namely, given program P, global state G, and a number K, is there a K context bounded run of P which reaches G? Right. So here, when I say global state G, I just mean some assignment of values to the global Boolean variables. So there are other problems that we can study. For instance, we can ask, is the task buffer always bounded by some number n? And does the program always terminate? So, and we can also ask whether, under the condition of fairness, whether it terminates or not, and so on. But in this paper, we focus on safety verification. And previously, what was known was that Atik, Bojani, and Kadir have shown that if the context switch bound k is given in unary, then the safety problem is 2x space, is in 2x space. However, there was a complexity gap, which we managed to fill in by showing that, in fact, this problem is 2x space hard quite recently. And unfortunately, one of the things is that the hardness proof uses many threads. And the natural question is that, is the problem easier with a bounded number of threads? So this motivates theoretically the notion of thread pools for us. Here we have an example of a thread pool where there are 4 threads. So here we see that in each of the threads, there is some task which is running. So this means that at this point, if we wanted to initialize some new task, then this is not feasible. Right? So this means that one of the threads must finish running whatever task it's running. And then only when there's an empty spot can one initialize this new task into that particular thread. So not only from a theoretical perspective, but from a practical perspective, thread pooling is important. It's commonly implemented in large-scale systems where there is a requirement for latency. And now notice that we have 2 different numbers, parameters. One is the context switch bound k, and the other is the thread pool n. So our results are as follows. So we show that the k context bounded n thread pool safety problem is in X space, even when the parameters k and n are given in binary. So this is really surprising, because we also show that suppose there is no thread pooling. So this means that just the k context bounded safety problem is 3x space complete when k is given in binary, right? So there is a another exponential blow up. And we also know that, in fact, the safety problem is X space hard already for the simpler model, which is a restriction of what we have seen in this paper called asynchronous programs, where it is a special case where k equal to 0 and n equal to 1. So what does that mean? It means that in asynchronous programs, you have just a single thread, n equal to 1, and it picks tasks and runs them to completion. So there are no interruptions, right? So k equal to 0. So, so these are our central results, and in the rest of the talk, I will outline the proof of the upper bound result. And I will do that by first looking at the obstacles to the proof given by Atik, Bojani, and Kadir for the unary, for k in unary problem of 2x space. And we will see how to overcome these obstacles using a new technique. And finally, we show our X space upper bound using a reduction to vector addition system with state coverability. So let's begin with the obstacles to the proof by ABQ. So the Atik, Bojani, and Kadir 2x space result goes as follows. So firstly, they note that the behavior of a single task can be captured by a task PDA. And the central idea in the paper is that safety is preserved under losing of spawns, right? So if you have a system And then you look at the behavior where there is some spawn which is just forgotten or not added to the task buffer. Then this gives you another system which still preserves safety. And this losing of spawns is captured by what is called the down closure abstraction. And in terms of languages, it is well known that given any language, if you take the down closure of the language, you get a regular language. In particular, the down closure of a pushdown language gives you a regular language whose representation in terms of NFAs is exponentially larger. And in fact, there is no way to do better, provably. And further, the paper goes on to construct a poly-sized vase, which counts the number of threads in each state of this NFA. Thus, they reduce the safety problem to vast coverability, which is known to be in X space. And together with this exponential blow up because of the NFA construction, they get a 2x space result. So now in our setting, K is in binary. So this gives a further exponential blow up. So this method, as is outlined here, would actually give a 3x space algorithm. And the question is, how can we do better? So the key notion that we introduce in this paper is that of succinct down closures. So what are these? So first we define a model, namely a succinct pushdown automaton, where an exponentially larger pushdown automaton is described in a succinct manner. And further, we show that it's possible to obtain the down closure of this pushdown automaton while retaining this succinctness. And further, we show that we can convert this succinct down closure pushdown automaton into a doubly succinct down closure NFA. So then we will show in the third point how to use this down closure NFA to finally achieve this reduction to vast coverability. So first, let's start with this notion of the succinct PDA. So succinct PDA, as defined by us, uses transducers. So here, the PDA has states which are represented by words W of length n. So even if you have an alphabet of just size 2, this means that the number of words of length n will be 2 to the n. So this gives us exponentially many states. Right? So now for every input letter A and stack operation V, we have a transducer TAV. And what we do is we allow the PDA, the succinct PDA, to move from a state W to a state W prime on input A and stack operation V, if and only if W comma W prime is in the language of this particular transducer, right? So this transducer tells you when this particular reading of A and operation V can be done, right? And you can move from W to W prime. So now, how do we apply this notion of a succinct PDA to our setting? So, of course, the behavior of a single task can now be captured by a succinct task PDA. And here, you can think of the PDA state as written out on a tape, as we see here. And the 1 and the 0 initially are values of the global variables at a particular point. And then there is a separator symbol dollar, further followed by the values of the local variables. So now when we have a transducer, TAV, which runs on this word, then it will convert this into some other word. And here we see that some changes have been made to the global and local variables. So in particular, in our setting, the input denotes either a spawning operation or is part of some context switch, right? So this is what we use for A. And note here that there are exponentially many different succinct task PDAs, simply because there are many different ways to initialize by setting the global variables and local variables to different values. However, this set can be represented compactly because the main structure, the internal structure remains basically the same. It's only the starting values which will be different, right? So this allows us to capture this entire set in a compact manner. So we have seen the succinct PDA and how it applies to our setting. So let's look at how we can get the down closure of this in a succinct manner. So first we note that we can actually get a bounded stack PDA for the down closure of a ordinary pushdown automaton. So we showed in our TAKAS 2021 paper that from a PDA P, one can construct in poly time a bounded stack PDA P top representing its down closure. So here the bound H on the stack of P top is quadratic in the number of states of the original P. But in our proof, the height bound for the stack is exponential because of the succinctness. And thus we get from a succinct PDA C in polynomial time, a succinct PDA C top and a number H in binary, such that the H bounded language of C top is precisely the down closure. So here notice that since H is in binary, so it can be represented in a small manner, but the actual value of H is exponentially large. So let us see how the bounded stack PDA is produced for in the case of a normal automaton, push-down automaton. The construction is by saturation, namely by adding extra edges. And the key idea is to drop letters which occur on positive loops on any state. So what do I mean by that? So consider a run like this, right, where we have drawn the stack height with respect to time. And suppose the stack height exceeds this quadratic bound that we mentioned, then it must be the case that there are states Q and Q prime which occur as shown. And the part of the run between the two dotted lines between Q and Q prime, this can be cut out by what is called a hill cutting argument. So this allows us to sort of make sure that the height is bounded. So this is the key idea. Now we have seen how to obtain this succinct down closure PDA, or at least some idea of it. Now, how do we convert it into a doubly succinct down closure NFA? This is very simple. So the states are for a doubly succinct NFA are exponentially long strings of length m. And here the number m is given in binary and is part of the description of the doubly succinct NFA. So this means that there are doubly exponential number of states in the size of the description, and this is why we say it's a doubly succinct NFA. So given a succinct PDA, so we see that there is a polynomial size state, but then there is an exponential size stack. But of course, both of these can be accommodated into the exponential state of a doubly succinct NFA. So thus, we have shown that from a succinct PDA, one can construct in polynomial time a doubly succinct NFA, which represents its down closure. So now how can we use this doubly succinct NFA? And what we do here is to define the notion of a succinct notion of VAS, namely transducer controlled VAS, using a doubly succinct NFA. And further, we show how to reduce coverability of such a succinct VAS to normal VAS coverability, thus giving us the X-phase result. So let's look at the definition of TC VAS. So as expected, the state transition is controlled of the TC VAS by a doubly succinct NFA. And there are two transducers per counter, one for the decrement and one for the increment operations of each counter. And the TC VAS runs n many task NFAs in parallel, right? So we have this thread pool of size n, and all of these are taken care of in the state of the TC VAS. So notice here that, of course, because n is given in binary, so there are exponentially many threads. Exponentially many such threads which are running. And each of these might have exponential size. But since these two multiply, this means that the entirety of this is still exponential in size. And this can be accommodated inside the state space can be stored inside the state of this TC VAS, which has an exponential size state. Okay? Further, the uninitialized tasks, remember that there is a task buffer which contains the uninitialized tasks. So these are kept track of in the counters of the VAS. Okay? So thus, we are able to reduce the safety problem to TC VAS coverability. And now let us see how we can further reduce this TC VAS coverability to VAS coverability. So the key observation is that the language of a TC VAS is the intersection of the language of its associated doubly succinct NFA, right? So there is the control mechanism with the Dyke language. So what does this mean? So the Dyke language is nothing but something that gives you sequences of counter operations where the counter does not go below 0, right? So if you just have an NFA, there are certain sequences of operations, which are basically the words accepted by the NFA, which could violate the condition that VAS places. So in order to avoid this, we intersect this with the Dyke language, and thus we get precisely the language of the TC VAS. So now, having separated the TC VAS into sort of its two components, one of them being the control and the other being the Dyke condition, we see that this A of V, which is the associated doubly succinct NFA, can in fact be replaced by a small VAS. And this is because an exponentially bounded NFA can be simulated by a polynomial size VAS. using the Lipton construction. Further, we see that this simulation it preserves the execution sequences, and this is of course important. So to conclude, with the context bound given binary, we have shown that the safety problem is 3x space complete. However, when we introduce a thread pool, this second parameter, then the complexity decreases to X space, even in the case when both of these parameters are given in binary, so which was very surprising to us. The key technique used in our result is that of succinct down closures, and we hope that these techniques can be used for related problems. Thank you.
Okay, thank you for the talk. And we have a couple of minutes for questions and answers. Any questions from the audience? Maybe let me begin with a quick question. So I'm wondering that whether or not your result are applicable to some languages with synchronization primitives.
So what kind of
I mean, with
synchronization
log,
primitive?
for example, logs and unlogs, and could your
Yes,
result?
so we can definitely implement locks via the global state. So this was a good thing, because I mean it turns out that because a single Boolean variable can be used for one lock. So if you have some fixed number of locks, then this would increase the number of global Booleans by some fixed amount. So this means that basically the complexity result doesn't change even if you add this.
Okay, thank you. Any other questions? Okay, thank you again for the talk. And